All right, so here's the second part of the Unit 3 Atoms and Elements. This is going to mainly we're going to talk about the history of how the atom was discovered. Who discovered what? Today we know there are protons, neutrons, and electrons, but who determined this and how did they do it? The first person to be given credit for the atom is actually Democritus in ancient Greece. However, he wasn't as influential as Aristotle. Aristotle thought this idea that there was a smallest particle, Aristotle thought it was crazy, and so most everybody rejected it at the time, so poor Democritus didn't really get credit for it. However, the word atom is derived from the Greek word atomos, which means indivisible, and so I guess eventually he was given credit for it. John Dalton was really the first modern scientist to propose that there was such a thing as an atom, a smallest particle that retained the same properties of the element. So he created the atomic theory that we'll look at the next slide, and he basically said that atoms cannot be altered or destroyed, but they can be combined to form more complex structures, which he called chemical compounds. And he believed that the atom could not be broken down any further. So the picture on the bottom right shows sort of John Dalton's idea of what the atom is, a solid sphere that couldn't be broken down any further. So here's Dalton's atomic theory. He noticed that matter always combined in fixed ratios, and so this is what made him get the idea of this theory, the Dalton's atomic theory. So Dalton's theory said that all matter is composed of extremely small particles called atoms, that atoms of given elements are identical in size, mass, and other properties, whereas atoms of different elements differ in size, mass, and properties, which we've already seen. Atoms cannot be subdivided, created, or destroyed. Atoms of different elements can be combined in simple whole number ratios to form compounds, and in chemical reactions, atoms are combined, separated, or rearranged. They're not changed, however. Dalton's theory was a huge breakthrough at the time. It seems common sense to us now, but there were eventually some errors discovered, which we've already talked about and which we'll look at again in a minute, but his theory as a whole is still accepted today. J.J. Thomson was the next scientist in our timeline, and he was actually the first to determine there were smaller particles inside the atom. He actually was the one who discovered the electron. He did some experiments using a cathode ray tube, which you can see a picture of here, cathode ray tube, which actually is the original televisions were cathode ray tubes. Anyway, a cathode ray tube, you connect electrical current to a piece of wire or some kind of element, and when that happens, a stream of particles are given off of that metal, and that is a cathode ray. When he put a magnetic field aside that the cathode ray, he discovered that it was drawn to the positive side of the magnet, which means that the particles themselves were negative. And so he, in fact, discovered the electron. The thing about Thomson, we'll go on to the next slide. The thing that Thomson found interesting is that the same ray of particles was present no matter what the element he used. And so he concluded the electrons were found in all atoms. He also concluded that they were over 1,000 times smaller than the proton in mass, in size. And And he also, so his idea of what the atom looked like, the picture on the lower right-hand side, was called the plum pudding model, because he knew there were small particles that were negative, and he knew that if something was negative, there had to be an equal number of positive particles to make the overall atom neutral, and he didn't know how they were organized, so he just sort of stuck them in there. So we call it, he was British, and so it looked like a plum pudding with raisins and other things stuck in there. So the main thing that Thomson discovered was the electron, that we can divide an atom into smaller particles, although it no longer is that element. However, that smaller particle, the electron, is found in all atoms. Rutherford was a student of Thomson, and he did some further investigations. He took a thin piece of gold foil and shot small particles, which are positively charged particles. Alpha particles are small positively charged particles. He shot them through the foil, and he detected where they ended up after they went through the foil. Well, most of them went through the foil. However, surprisingly, a few of them were deflected back the way they came. And you can read his comment. He stated that it was as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. So it was a huge surprise in the day. It contradicted the plum pudding method, and you can see in the two pictures, model. If you look at the plum pudding model, alpha particles should all pass through. However, since some of the particles bounced backwards, what that told Rutherford is there had to be something very dense inside the atom. And so he's basically the one who discovered the nucleus. This little video, YouTube video that I have a link to on my PowerPoint, which you may not be able to get it, but if you type it in, you may be able to watch it. And it's a pretty good little video that will describe how he set up the gold foil experiment. So Rutherford's atomic models said that all atoms have a nucleus. He determined that the nucleus was very small and dense, first of all, because most of the alpha particles went straight through. So that tells you that most of the atom is empty space. Since some of them came straight back at him, that's what made him determine that the nucleus was very dense and very solid. And also, some of the alpha particles were just bent a little bit, which also told him that all the positive charge was in the nucleus. So that's where the protons are. And since most of the alpha particles went straight through, he was able to determine that most of the atom was empty space, and the electrons were found in that empty space. So in just a minute, we're going to talk about how electrons are arranged. Actually, we'll look at them just briefly in this unit, and then also some more in Unit 4. But before that, we're going to talk about light and electromagnetic radiation. So wavelength and frequency. When we look at light is actually a wave of energy moving through space. It looks like the one here to the right, the red line. A wavelength is the distance between the top of one wave to the top of the next wave, or actually you can take any point along the wave, and if you measure to the exact same point on the next wave, you have the wavelength. So the distance between crests. Frequency is defined as the number of wave crests that pass a point in 1 second. So if you look at the bottom picture, if you kind of assume that the distance is maybe 1 second, how many waves pass us in 1 second, you can see that the red is approximately 3.5, the orange is maybe 4.5, the green is about 6 crests that pass, the blue is more than that, and of course the purple is more than that. And so frequency is just how many crests pass through a point per second. Now, all light moves at the same speed, the speed of light, so it's coming at you, but because of the wave, they have different energies. Each different type of light has different energy and different wavelengths. If you take white light, for example, and you put it through a prism, you've probably all at least seen pictures of this, it will bend the light into the different colors. And the reason why it does that is because each color is a different wavelength, and so they're bent within the prism to a different extent. Frequency and wavelength are inversely related to each other. What that means is that the longer the wavelength, the smaller the frequency, and vice versa. If the frequency decreases, the wavelength increases. If the wavelength decreases, the frequency increases. So if you look on the picture on the right, you can see that the blue wave has a longer wavelength and a lower frequency, whereas the brownish red wavelength is much shorter but has a higher frequency. There's more crests per unit per distance. Also, if you kind of look at the colored on the previous slide or above on the prism, red light has a longer wavelength and a lower frequency. Purple light or violet light then has a much higher frequency and a shorter wavelength. So they're inversely related. So frequency and wavelength are inversely related. However, frequency and energy are directly related. So what does that mean? That means if you have high frequency, which is connected to a short wavelength, then you also have high energy. If you have a long wavelength, which is related to low frequency, you have low energy. So again, looking at our spectrum, the red, which is the longest wavelength, has the lowest frequency and therefore the lowest energy. The violet has the highest energy because it has the highest frequency and the shortest wavelength. Now, visible light is only one small part of a continuous range of wavelengths and frequencies. So it's only a very small part. So we'll look at the next slide. We'll be able to see exactly how visible light falls in the whole spectrum. So this is the electromagnetic spectrum, and you can see it goes all the way from the left, which are gamma rays, X-rays. UV is ultraviolet rays. And you can see the color is just a very small portion of this whole electromagnetic spectrum. They've taken it and they've expanded it so that you can actually see the wavelengths of the different color visible light. On the other side of the red is infrared and microwaves, radio waves, and long radio waves. So what I want you to notice is that going from left to right, we have increasing wavelength. So the wavelength is getting larger and larger. But going in the opposite direction, going from right to left, we have increasing frequency. So there's the inverse relationship. And of course, going from right to left, increasing frequency also is increasing energy. So as I'm sure you know, gamma rays and X-rays are very high energy wavelengths, whereas radio waves, they're pretty benign. They're very long and have very low energy. This is an interesting little picture. It tells you kind of how long a wavelength is for different types of energy. So gamma rays, which is the highest energy, has the very smallest wavelengths, and they're actually so small that they're on the about the size of a nucleus, an atomic nucleus. X-rays are a little bit longer in wavelength, and they're about the size of an atom. It's still something we can't really get our heads around, but they are a bit bigger. Ultraviolet light, as you can see, is more on the size of a molecule, so a bit bigger. Visible wavelengths are about the size of the amoebas, those very small one-celled organisms. Infrared is even bigger. It actually starts to get into the visible range where you can see a needle point. Microwaves are even longer. And radio waves can be as tall as humans or even as tall as buildings. Skyscrapers can be as long as a football field. Also notice, I meant to see that on the previous slide, but also notice that red light we saw this earlier, the red light has the longer wavelength and the lower energy. The blue light has the higher energy and the shorter wavelength. And so it's sort of a nice little picture. So if you take white light and you put it through a prism, as we saw a few slides ago, we'll produce a continuous spectrum. You see the whole rainbow of colors. But what happens if you take a particular element and heat it up and produce light? Think like a neon lamp, which is only has neon. Well, what happens is if you take light just from a particular element and you pass it through a prism, you get what's called an atomic spectrum. And these are pictures of atomic spectra down below. It's basically black except for a few lines of color. This means that only certain wavelengths of light, or again, certain wavelengths relating to certain energies, only certain energies and wavelengths of light are produced when an element is heated, not the full spectrum. Hydrogen, you can see here, only gives off it looks like maybe 3 really dark blue lines, a light blue line, and kind of a peachy line. Helium has a number of more lines, purple, blue, kind of an aqua, orange, red. Every element has a different atomic spectrum. So Bohr was the next scientist that you should know about, and he's the one who basically figured out how electrons were organized within an atom, so the electronic structure of an atom. So by using those atomic spectra, he proposed that electrons could only exist at certain energy levels in an atom. So there you can see my little sort of flat electrons sitting on the different lines. They can't exist between lines, but only on the lines. They can, however, jump between the lines. So it's sort of like if the difference between walking on a ramp or standing on steps. You can't hang out halfway between two steps. You can only exist on one step or the next step, but you can jump between steps. So the same thing here, these electrons can move between the different levels. Now, if an electron goes from a lower level to a higher level, then that means that energy has to be absorbed to make the electron jump from a lower energy level to a higher energy level. That's the blue line in the upper right-hand corner. Now, if an electron goes from a high level down to a low level, what happens is energy is released. Now, those distances will relate to very particular wavelengths, and so that's why there's only certain jumps in energy that an electron can take, and so that's why only certain wavelengths can be seen from every different element. Different elements will have different energy levels, and so each element has a different spectrum. And just for your information on the side, that this is how astronomers can actually identify elements in distant stars. They're able to take an atomic spectra of a particular star or planet, and they can see those spectra and can compare it to what element would give off that particular spectrum. The main thing that you should know here is Niels Bohr determined that electrons could only exist at certain energy levels. Now this kind of looks like sort of like a solar, an orbit that electrons are spinning around, and that's what he thought at the time. Now we know that's not exactly true. So actually our current model is called the quantum mechanical model, and it's taken Bohr's model and made it a little more convoluted, actually, from a student's point of view. But it's mostly right. Electrons are not quite as straightforward. They don't circle a nucleus the way it looks like. A precise path of an electron is something that can't really be determined accurately. So we know it can change speeds, it can change direction, and so instead of circular orbitals, what we have are instead of circular orbits, what we have is something called an atomic orbital. That says where an electron can be, and we're going to really look at that more in Unit 4. So this is really the end of Unit 3. So you should be able to identify. You should be able to identify the names of the different scientists and what they're generally given credit for discovering. So Dalton determined that there was a small particle called the atom. Thomson discovered the electron, and he had the plum pudding model. Rutherford determined that there was a nucleus where the protons were located in the nucleus and mostly empty space. And then Bohr determined that electrons could only exist at certain levels. And we'll look forward to Unit 4.